Thank you, Nick, for the introduction, and thank you to the organisers for the opportunity to speak here today. Unfortunately, my PhD came a year too late to have the pleasure of meeting Fred, but his work's been a great inspiration to me, and it's been great to hear all the stories across this week and last week about what a great man he was. So I'm going to talk about Anick's conjecture for polyhedral products, and all the new results in this talk will be based on joint results with Fedor-Valijanin. And I guess a good starting point is to talk about what Anick's conjecture is. If my PowerPoint will work. It's not. There we go. So as Reggie spoke about earlier, one thing we like to know about is the homotopy groups of a space X. And one way to do this is to try and find a decomposition for the pointed loop space of X into a product of spaces, hopefully for which we know more properties of the homotopy groups of the space. And more what we might hope for is that this decomposition is into a bunch of indecomposable spaces. And the thing to note here is that each of these Y alphas will retract off of the pointed loop space of X. So in particular, we'll have an induced H space structure. And so the first thing we'd like to do is try to find examples of indecomposable H spaces, which could appear in such a decomposition. So the first obvious examples are spheres of dimensions 1, 3, and 7, and loops on simply connected spheres of dimensions 2, 4, or 8, with the dimension restrictions, of course, being where we have elements of Hopf invariant 1. These all have torsion-free homology, but if we want some torsion in homology, then Cohen, Moore, and Eisendorfer defined these spaces here for an odd prime P, and Fred Cohen did it for primes 2, where your power is greater than or equal to 2, for which the loop space of the corresponding Moore space decomposes as a finite type product of these spaces. And most of these are indecomposable, with a single exception to T3P, which decomposes as another one of these T spaces, crossed with another space U1, which is itself an indecomposable space. So now these are all integral indecomposable H spaces, but something we can do to make things easier is to localize at a prime P, and that's a functor which gives us a new space, which will just tell us about the P torsion information in the homotopy groups, 1 prime at a time. And if we localize at an odd prime, then actually all of the odd dimensional spheres become H spaces, and the loops on even dimensional spheres will all become decomposable spaces into the product of an odd dimensional sphere and the loops on an odd dimensional sphere. So with the localized picture in mind, we'll let P be the collection of spaces which are odd dimensional spheres, loops on odd dimensional simply connected spheres, and these Cohen, Moore, and Eisendorfer spaces that I mentioned a second ago. And the conjecture of Anick is that if you have a finite simply connected CW complex, then if you localize at almost all primes, meaning all but finitely many, then the conjecture is that the loop space of X decomposes up to homotopy as a product of spaces Y alphas, where each of these Y alphas are in this collection P. So the point is that if you have a finite simply connected CW complex and you fix a large enough prime, then to understand the P torsion information within the homotopy groups of X, it should hopefully be enough to understand the P torsion information within these spaces in P. And just as an example of how things can change when you localize at different primes, if you localize at the prime 2, then the loops on S6 is an indecomposable space. But when you localize at an odd prime, as I kind of already mentioned, then the loops on S6 decompose as a product of an S5 crossed with the loops on S11. And there's been various examples for which this conjecture has been verified. The classical example, which obviously predated this conjecture, is the Hilton-Milner theorem, which decomposes the loops on a wedge of spheres as a product of looped spheres. Finite rationally elliptic spaces was shown by Wilkinson of Gibbon in '86. And as Reggie spoke about earlier, there's been lots of work in the context of highly connected Poincare duality complexes or manifolds, which you can recover decompositions of these kinds in those cases. But what we want to talk about here is polyhedral products, and I know we've seen the definition a few times this week, so I will just quickly go over it. And for the polyhedral product, we have two ingredients. So the first of which is a simplicial complex on the vertex set from 1 to m. And for each of these vertices, we will have a pair of pointed CW complexes. And then for each of our faces of the simplicial complex, we'll define an initial space, which will be a product of yi's, where we insert in an xi if I is within our given face, and an ai if I is not within the given face. And then the polyhedral product associated to K is simply just the union of all of these initial spaces over all the faces of our simplicial complex. And this gives us a nice subspace of the product of the xi's. And the case that we're going to be interested in, at least to start off with, we'll look at some more general ones later, is the moment angle complex, which I'm sure we're all familiar with by now. But I thought I'll just go through a couple of examples before we look at looping about how the homotopy type of these can change. So if we take K to be two disjoint points, then we can go through the definition. And from the first vertex, we get a D2 crossed with an S1. From the second vertex, we get an S1 crossed with a D2. And then from the empty set in the simplicial complex, we get an S1 crossed with an S1, and that's what we're going to take the union over. And that simply just gives us a copy of S3. So now if we move on up a bit, and we take K to be the boundary of a square, well, you can see the boundary of a square as the join of two sets of disjoint points. And in general, if you have a join of simplicial complexes, then the corresponding polyhedral product will just break up as the product of the corresponding polyhedral products. So from the previous example, in this case, we just get a product of two S3s. And then even if we just insert invertices in this to get the boundary of an n-gon, then a result due to McGavran, which predated the notion of moment angle complexes, but if you translate it into this language, you get that in this case, it's actually a smooth manifold, and it's actually diffeomorphic to a connected sum of sphere products in this case. And in the manifold case, there are some other examples where it's known you get a connected sum of sphere products. And there are some examples where you get a product of three spheres in there, for example. And from that, you can generate some examples of moment angle manifolds, which break up as a connected sum of manifolds, but don't necessarily have, one of them isn't necessarily a connected sum of sphere products. But outside of that, not much is really known about the homotopy type of these moment angle manifolds. But moving out of the case of manifolds, there is some stuff we can say more generally. And to do this, I will just set up some notation. And this is that if we have a collection of spaces X, then we'll denote by the product of X, or the wedge of X, to be the collection of spaces which are homotopy equivalent to a finite type product or wedge of spaces in X. This is slightly different notation to the one Brian used, but the idea is the same. And the first two collections we will look at is W being the collection of simply connected spheres, and we'll let P be the collection of loops on simply connected spheres. And there was a big scheme of work trying to find different families of simplicial complexes, for which it's known that the moment angle complex decomposes up to homotopy as a wedge of spheres. And just as some examples, there were shifted complexes, which are shown by Gerbich and Terrio in 2007. And this includes, for example, the K skeleton of a simplex. Flag complexes with caudal one skeleton was shown by Gerbich, Panov, Terrio, and Wu. And more generally than this, it was shown by Irie and Kishimoto for a class of simplicial complexes called totally fillable complexes. But the point of this for what we want for loop spaces is that if you know that your moment angle complex is homotopy equivalent to a wedge of spheres, then the Hilton-Milner theorem implies that the loops on the moment angle complex decomposes as a product of looped spheres. But we've seen the example of the boundary of a square, which is definitely not a wedge of spheres. It was an S3 crossed with an S3. But of course, after you loop, it will still be in this collection. And so this collection is a much wider family of simplicial complexes. And a big scheme of work recently has been in terms of trying to find families of simplicial complexes for which this kind of decomposition happens for looped moment angle complexes. The first one is where K is flag, which is shown by Panov and Terrio. And I generalize this through different methods to the K-skeleton of a flag complex. And one interesting note to point there is that the one skeleton of a flag complex can be any graph. So this in fact holds for any graph. Brian E. Eldridge spoke about on Monday about looking at when this collection P is closed, undertaking certain polyhedral joins. And then if you move up to the two-dimensional case, I show that under certain circumstances, you get that these are in P. And this case is actually part of a slightly wider decomposition where you can get one for any two-dimensional simplicial complex. And in those cases, if you have some torsion, you do get these Cohen-Moore and Eisendorfer spaces showing up, as well as some indecomposable two torsion spaces as well. And finally, for the manifold case, if K is the triangulation of S3 or a neighborly triangulation of S2n plus 1, then me and Stephen Terrio showed it's true for these as well. So there's a couple of points that I'm going to note here. So the first four on this list here, these actually hold for a slightly wider range of polyhedral products, those where you take your pairs to be cone on AA, and you know, for example, the suspension of your AI is homotopy equivalent to a wedge of spheres. But this last one here, we really did use the structure of a manifold in order to prove this. So this a priori only holds for moment angle for the moment angle complex case. But as we will see later, that actually for all these other polyhedral products that I just mentioned, you can actually reduce down to the moment angle complex case, and it will suffice just to study that case to show the decompositions for all these other polyhedral products as well. And the other thing to note in the context of Anick's conjecture is that all of these results are integral results. And what we want to do today is to see how much further we can push this if we're willing to localize away from some primes. So to do this, I'll just set up a tiny bit more notation. And if we have a space X, then we'll denote by tau of X to be the set of primes which appear as P torsion within the homology of X. And I'll say a few more details about this in a bit, but the first thing that Fedor and I did was to show that this set for looped moment angle complexes is actually a finite set. And in fact, we showed it's bounded above by something crazy like 2 to the power of n times 2 to the m or something massive like that. But it's a finite set, so we're happy that it's finite because we like finite things. But the point is that we use this to show that if you have any simplicial complex K on M vertices, and you let P be the collection of primes appearing as P torsion in the loop homology of these moment angle complexes, and any prime strictly less than 2n, then when you localize away from these primes P, you actually get that the loops on these moment angle complexes decomposes as a product of looped spheres. So I'm going to go through some details of the proof, not in detail, but I'll go through the steps that you need. And there's a couple of key facts that we will need that have appeared throughout the week. And the first of which is that we won't study the moment angle complex directly, but we will study a closely related polyhedral product called the Davis-Januszkiewicz space. And this is where you take your pair of spaces to be CP infinity and a point. And this is a subspace of the product of CP infinity, so we can include this in. And when you take the homotopy fiber of this, you exactly recover the moment angle complex. But what's more than that, this homotopy fibration splits after looping. And so in particular, the loops on the moment angle complex will retract off of that, of the loops of the Davis-Januszkiewicz space. So any properties that we prove about the DJK, we can lift back down to the moment angle complex case. In particular, for being in P, this collection P is actually closed under retract. And so that's all we would need there. And the second thing is that if you look at the loop homology of the Davis-Januszkiewicz space, this is actually isomorphic to an extension algebra over the Stanley-Reisner ring, where the Stanley-Reisner ring is where you take the polynomial ring on m variables and you quotient out by monomials corresponding to missing faces of your simplicial complex. And so I'll go through the steps. And so the first step was to show that this set was finite. And the way we did this is that Berglund actually studied the Poincare series of these X algebras over any monomial ring. And you can actually write this in terms of the Poincare series of the homology of some auxiliary simplicial complex. And in the case of the Stanley-Reisner ring, this simplicial complex has the vertex set being the minimal missing faces of the simplicial complex. And the point is that if you take P to be a large enough prime, then to get P torsion within the homology of the simplicial complex, then you need enough vertices in there to be able to generate this P torsion. So in particular, because the number of vertices in this simplicial complex is bounded, if you take P to be large enough, the Poincare series, the Z mod P Poincare series will be identical to the rational one. And so therefore, by the universal coefficient theorem, there mustn't have been any P torsion within the homology of your space. So the second thing is to show that in 1 over P local coefficient, then the homology of the loop space of djk is generated by elements of degree strictly less than 2m. And I'm not going to go too much into this, but you can show that if you study this Tor algebra, then the set of additive generators of this will give a multiplicative generating set of this 1 over P local loop homology. And you can show that, of course, then they would be generated by elements of degree strictly less than 2m in this case. The third thing is that rationally, we have the Milnor-Moore theorem, which gives us an isomorphism between the universal enveloping algebra of the rational homotopy groups and the rational loop homology. But Anick showed that there's a P local version of this, which is well defined up to certain degrees, as this is for subrings of Q, I mean. And if you take P to have enough primes in it, which would be strictly less than 2m in our case, you could show that this is actually an isomorphism in these degrees. And the point of this is combining 2 and 3. Oh, and I should say this is induced by the Hurewicz homomorphism as well. But the point is that combining 2 and 3, we can start to define maps from spheres, which will hit these multiplicative generators. And these will then have an extension up to the loops on a wedge of spheres. And because these are multiplicatively generating the loop homology, you'll obtain a map which is a surjection in P local homology. And in particular, on the right-hand side, by the Hilton-Milnor theorem, this would decompose as a product of looped spheres. And with a bit of fiddling around, you can find a subproduct of these, which will actually give you a homotopy equivalence, where in this case, we get a product of S1s crossed with some other space, which is a product of looped spheres. And therefore, using this retraction of the loops of the moment angle complex of the loops of the Davis-Shenishkevich space, you can conclude the same thing for the moment angle complex case. So this is for the moment angle complex case, and this verifies Anick's conjecture for that, but we want to be able to do this for some more general polyhedral products. And in fact, we can do this for polyhedral products, which will involve some torsion in there as well. So to do this, I'll define a couple more collections. And the first of which is M to be the collection of odd primary Moore spaces of the form of dimension greater than or equal to 4. And we'll let T be the collection of these Cohen-Moore and Eisendorfer spaces where P is an odd prime. Now, I'll just say here is you can say some things if you have 2 torsion in there, and you can say things if you have 3-dimensional Moore spaces. But things get a bit more fiddly there, and I'm going to go through the proof. So just to make things simpler, I'm just going to restrict to these cases here. And the point is if you again have any simplicial complex and you have some spaces such as their suspension is a wedge of spheres and Moore spaces, then if you know that the associated moment angle complex is a product of looped spheres, then you can show that actually all of these polyhedral products decompose after looping as a product of looped spheres and these Cohen-Moore and Eisendorfer spaces. And so I'll go through a proof, and we're going to do an induction. And we're going to do induction on L, which will be the number of AIs which are not homotopy equivalent to S1. So the base case is where L is equal to 0. And in that case, all of our AIs will just be homotopy equivalent to S1. And so therefore, we get the corresponding polyhedral product is just the moment angle complex up to homotopy. And so we just have the result holding by our assumption. So the next thing is to assume L is greater or equal to 1. And we're going to pick out a space now, which is not homotopy equivalent to S1. And what we're going to do is we're going to define a different collection of spaces where we replace this AI with an S1 and leave all the rest the same. And this will allow us to apply the inductive hypothesis to show that decomposition holds. And then we're going to try and fiddle about a bit to try and apply it to the original simplicial complex, to the original polyhedral product, sorry. And the way we do this is that there's this result of Panov-Ontario, which decomposes the loops on any polyhedral product, but in this case for the colon YY, we will want associated to K in terms of the one for the restriction, where we've removed the vertex I, and this homotopy fiber F, which is in terms of the link into the restriction. And the point to note here is that obviously none of this has a dependence on the vertex I. And so actually this polyhedral product for the restriction is actually the same one as we had before for the restriction, and the same for the one for the link as well. So with that, we get a decomposition that looks like this. And the inductive hypothesis, because now we've got one more S1 in there, implies that the decomposition that we want holds for the colon YY for K. And both of these spaces in the product are going to be retracting off of this, and you could show that these collections are closed under retracts. And so the one for the restriction also has this decomposition, and as does the right-hand term. But because we have a loop suspension in here, you can use the James splitting to show that actually the suspension squared of F must be homotopy equivalent to a wedge of spheres and more spaces. So now what we can do is apply this result of Panov-Ontario again, but now to the case of the colon AA. And the only real difference here is now that this F is smashed with an AI. So you should think of this suspension squared here as having the suspension and this AI being smashed with being an S1. And we've already shown that this restriction has the decomposition we want. So now we just want to study the right-hand side. But now if we shift the suspension coordinate, where if we shift the suspension coordinate over to the AI, well, by assumption, this was just a wedge of spheres and more spaces. So now you can distribute these all over the smash, and this decomposes a wedge of iterated suspensions of F and smashes of more spaces with F. But we already showed that the suspension squared of F is a wedge of spheres and more spaces, and for dimensional regions, then all of these iterated suspensions will be, because these MJs will be greater than or equal to 2. And again, for the dimensional reasons where I said that these will have dimension 4 and above, you can again shift around some suspension coordinates to show that this right-hand side is a big wedge of more spaces. So therefore, this whole thing is a wedge of spheres and more spaces, and if you take the loops on that, you exactly obtain the collection of P union T. And so that's how we obtain that for the right-hand side. Right, so that does that for all of these, but Anick's conjecture was in terms of finite CW complexes. So we want to see if we can apply this to any finite CW complex. And this uses the first lemma up here, which is if you have a finite CW complex of dimension D and connectivity S, and if you localize away from primes appearing as P torsion within the homology of X and primes less than this quantity here, then you can use a homology decomposition to show that after suspending, it will be a wedge of spheres. And kind of the idea of this is that you have a suspension here. So after suspending, that will get rid of any of the Whitehead products which appear in your attaching maps. And then you're localizing away from any primes which would be appearing as P torsion within the homotopy groups of the attaching maps. But then using this, now if we take any collection of spaces A1 up to AM, and if you let P be the set of primes which appeared as P torsion within the loop homology of your moment angle complex, P's which appeared in the lemma above, and all the P torsion which appeared in the homology of each of these AIs, then if you localize away from P, then the loops on this polyhedral product will decompose as a product of looped spheres. And the reason for this is from the first lemma, after suspending and localizing away from these primes, we have that these are a wedge of spheres. And we showed when we localize away from these primes already that Anick's conjecture holds for these, and in fact we get a product of loop spheres, and therefore the previous result implies that it holds for these polyhedral products. So I can't remember exactly what time I actually started. I don't know how much time I actually have left.
I guess you could take a few minutes more if you want.
Okay, thank you. Yeah, so there's two other applications then, which I will just quickly breeze through. And the first is toric orbifolds, which I know we've seen a lot of this week. And these are closed, smooth, two-n-dimensional orbifolds, which have a smooth and locally standard Tn action. And the orbit space of this will be a polytope, which, just to set up notation, will be an n-dimensional polytope with n facets. And if you have one of these toric orbifolds, then a model up to homotopy is as a quotient of a moment angle complex by some subgroup of the torus, which acts almost freely on the moment angle complex. And this quotient description gives us this homotopy fibration in terms of the Borel construction. And what me and Fedor showed is that if you have one of these toric orbifolds, which is simply connected, then the first thing we need to know is that the set of primes which divide the order of all of the stabilizers is a finite set. And then if you localize away from this set, then actually the Borel construction is homotopy equivalent to this quotient, and therefore the toric orbifold and this homotopy fibration will split. And because it's simply connected, this subgroup must be a closed connected subgroup of the torus, so will just be some subtorus as well. So in particular, if you localize away from enough primes, this will allow you to verify Anick's conjecture for these spaces as well. And I'll just say in words, just to finish off, is that the technique that we used to reduce the cone on A case down to the moment angle complex case, or maybe I'll just put it on the screen, is that you can actually use this to reduce the calculation of the Poincare series of these polyhedral products as long as it's simply connected down to the moment angle complex case. And as I mentioned, Berglund described these in terms of some other simplicial complex, which is what these B hat KJs and Ks are. And so you can describe the Poincare series in terms of these simplicial complexes and the Poincare series of your ingredient spaces. And I'll just mention as an example, these have been explicitly calculated. In some cases, for example, by Lee Tsai, we show that if K is flagged, then you can write this in terms of the Euler characteristic of your simplicial complex. And I will stop there.